We will continue our lectures on bipartite network. We will pick up from where we left yesterday. So, the last thing that we discussed was, can we propose a model that will explain the structure of some of the collaboration networks. In particular, we were looking at networks like movie actor network or article author network, that is the scientific collaboration network. And what properties we were trying to explain by these generative models. So, one property we wanted to explain was the degree distribution of the bipartite network, especially the degree distribution of the actor nodes, because empirically we observe that the degree distribution of the movie nodes, which is shown here, is exponential in nature. So, it is more or less the case that most of the movies have degree very close to the average degree and there is very little variance. So, that is not interesting, and also we know that how you choose the cast size for a movie may not be physically also a very interesting phenomenon, that depends on the script and all. But how some actors become very famous whereas others are not, so might be an interesting social phenomenon which we can study. So, typically we are interested in studying the degree distribution of the actor nodes. So, which people have found is almost a power law with some cutoff. And also the another degree distribution that we would like to match is the one more degree distribution of the actor network. So, there actors are the nodes and you will have an edge between them if they have collaborated or co-starred in a movie, the number of movies they have co-starred, that is the weight. And again, if you try to find the degree distribution of those networks, that is the one mode projection, you find that it is a power law, it closely resembles a power law. And to explain this, to propose a generative model for such network, Ramasco et al. Proposed a model, and this model is again based on the very concept of preferential attachment. We know that in unipartite networks, preferential attachment gives rise to power law degree distribution. So, that is the intuition that perhaps for bipartite networks also preferential attachment will give rise to some kind of power law distribution. So, the details of the model is as follows. So, you have a partial network, that is you have certain movies already out there and some actors who have already worked in these movies, and naturally you have the edges connecting the movies and the actors. So, this is a partial network, and at this stage one new movie comes in. So, at every time step one new movie enters the picture, which means a new node in the movie partition is added, and this movie will have n actors. This number n can come from a distribution. In that case, we will choose some exponential distribution, or for simplicity we can assume that n is fixed and fixed at the mean of the distribution. So, you can assume that n is equal to some mu, where mu is the mean of the distribution. So, all movies have same number of actors, which is mu. Now, out of these n actors, m are new. Again, m can come from a distribution, or you can assume that m is a constant. So, it might be the distribution of that particular, the mean of that particular distribution from which m is drawn. So, there are m new nodes added to the actor partition. These are the debuts, the actors who are acting for the first time, and you connect this new node to all these new actor nodes. So, connect this new movie node to all these new actor nodes, m new actor nodes, and then you have to choose how many extra actors for this particular movie, n minus m. So, the movie has n actors, you have already chosen m who are new. So, you have to choose n minus m from the old actors, and how do you choose it? It is here where you apply the preferential attachment, and the preferential attachment is purely based on degree. So, you count the degree of each of the actors, normalize it by the sum of the total degrees of all the actors, and that gives you the probability of choosing a particular actor. So, I am not going into the details, because you already know the preferential attachment model for unipartite networks. It is exactly the same. Here you choose based on preferential attachment, not one node, but n minus m nodes, and connect to them. So, in this way you continue growing the network. Now, the question is, will this network generate the same kind of distributions that we observe for the real world movie actor networks. So, before going into the simulation, let us see if we can analyze this model a bit. We want to mathematically analyze and try to prove some properties of the model. So, how many movies are there in the network finally? So, think that initially we start with no movie, no actor kind of a situation. Then in that case, how many movies are there, movie nodes? It is equal to the time till which you simulate, because I said at every time step a new movie comes in. So, if you simulate for t steps, you have t movies. So, total number of movies is something like t. We represent it by t because it's sort of analogous to a concept of time, discrete time. And then how many actors do you have? Right. So, usually at every time step m new actors are added. So, if n is the capital N is the total number of actor nodes, then at every time step n becomes the previous n plus m. So, this is the process, and for sufficiently large t actually it will be almost equal to empty, because it will be empty plus some small number of the initial actors. So, it will be, you can approximate it by empty. So, that is the number of actors or nodes in the actor partition at time t. Now, can you tell me what is the number of edges in this network? So, there are t movies and every movie has n actors. So, it will be n t. So, we can assume that n is fixed at some mu, as I said, is rather than coming from some distribution, let us assume that it is fixed at mu, then the number of edges are mu t. Now, tell me what is the average degree of an actor node? Mu t by m t, which is mu by m. So, therefore, the average degree of the actor is mu by m. Is not it interesting? You see, both the networks are growing, both the sides of the partition are growing, and you are choosing preferentially. So, some actors will have a very high degree, some will have very low degrees of course, but even then no matter what happens, the average degree remains constant and throughout this evolution process. So, no matter for how long you simulate, the average degree is always mu by m, it is constant approximately of course, because you have those small numbers that we initially neglected, but as time progresses it converges to mu by m. So, that is the average degree of an actor in the bipartite network. What is the average degree of the actor in the one mode projection? So, if an actor has a degree q in the bipartite network, and if it has a degree k in the one mode projection, what is the relationship between k and q? K is equal to mu minus 1 into q. We saw this yesterday. So, if this is the case, now can you tell me what is the average degree of an actor node in the one mode projection? Can't you write this? This is a constant. So, can't you write this? And if you can write this, it will be like this. So, the average degree of the one mode is also fixed. It converges to this particular value as time progresses. So, these are two very good properties of the degree distributions. Since the average degree is fixed, actually you can assume a lot of things about the evolving degree distribution. So, this is about the average degree, but now suppose I want to find out how the degree distributions look like. So, what I want to find out is this function q, which is the degree distribution of the actor nodes in the bipartite network, and this function k, which is p, which is the degree distribution of the actors in the one mode projection. I want to find out the whole function. How do you do it? I am not asking you for the solution. What is the process? What is the procedure for getting this analytical solution? It should be the same as you do for as you have done for the Barabasi-Albert model in for unipartite networks. So, what do you do? Have you heard of something called a Markov chain? Some recursive equation you want to write about the degree distribution, which might also be called the Markov chain or the Markov equation, the evolution equation. There are various names. So, that rings a bell. Okay. So, let us do a very simple exercise. So, Q is the degree distribution of the bipartite network. So, let us first try to solve for Q. What is Q1 at time t? Tell me first the physical significance of Q1 at time t. It will tell me the fraction of nodes in the bipartite network, actor nodes in the bipartite network, which has degree 1 at a given time t. So, how does it depend on things like, so what are the things it will depend on? It will depend on this, the fraction of nodes which had degree 1 at time t minus 1, how many were already there, and what else? Definitely m, but these are fractions. So, we need to convert them to actual number of nodes. So, let us multiply it by n t, the total number of actor nodes at time t, then this quantity is the number of nodes with degree 1 at time t, and this should be multiplied by. So, this is the number of nodes with degree 1 at time t minus 1, plus how many new nodes were added. Let us take m to be constant. So, m new actor nodes came in with degree 1. These are all debut actors, all of them have degree 1. Is it all, or you need to do something more? What do you want to subtract? Gets a higher degree, and how many such nodes will get a higher degree? So, there are already these many nodes, and they will be selected, each of them will be selected with a preference of 1 by, so the degree is 1. So, the preference is based on the degree. So, 1 by the normalizing term, the summation of all the degrees. And what is the summation of all the degrees at time t minus 1? No, mu into t minus 1. At time t minus 1, there are t minus 1 movies, each has mu degree. So, total number of edges in the graph is mu t minus 1. So, the sum of the degrees of all the actor nodes is mu t minus 1. Right, I will tell you why I am subtracting this, but you need to multiply something more to it also. So, this is if one node was chosen, but the movie is choosing how many such nodes preferentially? N minus m. So, n we have chosen to be fixed at mu. So, it will be mu minus m. Okay. So, the question is why we are subtracting this quantity. So, think it in this way. So, suppose this is at time t minus 1, say m is equal to 2 and n is equal to say 4. So, this movie came in first and then this movie came in. So, this movie came in with all 4 new actors, and then when this movie came in, it chose 2 new and 2 old ones. Now, a third movie comes, and at this point of time you want to write this equation in terms of the previous situation. So, what is the previous situation? What is n t minus 1? It is 6. Actually, it should be empty, but since it is the beginning of the simulation, so this term dominates, this extra 2 nodes are dominating, but that is fine. N t minus 1 is 6. And what fraction of nodes have degree 1 already? So, it is 4 by 6. So, this term actually gives nothing but 4. It says there are already 4 nodes which are of degree 1 in the graph. So, they remain to be degree 1. As soon as I add this will choose 2 new nodes as per the rule. Remember, m is equal to 2. So, these 2 new nodes are added. So, I add plus 2. So, 4 plus 2 is 6. Okay. So, I already have 6 nodes 1, 2, 3, 4, 5, 6 nodes of degree 1. However, this will also choose 2 old nodes, right, preferentially, and when it chooses 2 old nodes, suppose it chooses this node. As soon as it chooses this node, its degree now becomes 2, it is no longer a degree 1 node. Therefore, you should subtract this particular node from this 6 to get the, suppose it had chosen this 2. So, ultimately you should subtract this node to get this quantity 5, that actually there are 5 nodes at the time t which has degree 1. But how do you determine what is this quantity, what is the expected value or number of nodes with degree 1 that are preferentially chosen by this particular incoming movie node? That is given by, what is the probability of choosing one particular node? That is nothing but the preference, which is k by sigma k. So, k is here 1, and what is sigma k? It is nothing but mu t minus 1, because there are total t minus 1 nodes. This is probability of choosing one node, but there are how many such nodes, because it can choose any one of them. So, the probabilities add. So, there are q t minus 1 into n t minus 1 such nodes. You are multiplying, because there were already 4 such nodes. So, basically you are multiplying by the term 4, and then finally it is not choosing only one such nodes. So, this is the proportion of the nodes on the expected value of the node fact that this particular edge land up on a node which has degree 1. So, it now becomes degree 2, but then there are many such edges. How many? Typically n minus m, which is 2 in this case. So, there will be another edge. So, in general there will be n minus m such edge. So, you sort of multiply all this quantity to get the value and subtract it from the equation to get the final number of nodes with degree 1. And now you can do some simplifications, like n t minus 1 you can approximate by m mu t minus 1, and similarly yeah, that's I think the only approximation here you could do, and n t you could approximate by mu t, and after that you can rearrange all these things. That is fine. Now, what happens after that? You get some equation of value of q t 1 in terms of q t minus 1. What happens after that? So, you can express q t 1 as a function of q t minus 1 and mu m t, etcetera. But what do you do after that? How do you solve this equation? Yeah, this is the recurrence relation. So, you could apply several methods to solve it. So, one particular assumption really helps us to solve these particular cases. The assumption is when t tends to infinity, what happens? It converges. So, therefore, what should happen? q t 1 should be equal to q t minus 1. When it goes to infinity, when at large time the distribution never changes no matter how many movies you go on adding, and this is guaranteed by the fact that the average degree is fixed, it is not diverging. So, the distribution also goes to a fixed point, that is the stationary. So, you can relate all this actually, this is related to the concept of random walk. So, since it is a Markov chain, q t is only dependent on q t minus 1, what was the previous state of the network. So, it is a Markov chain, one step evolution at every point, and there is a method which I can't cover in this, but there is a method where this Markov chain is written in terms of a matrix multiplication. It is a linear equation, so you can write it in form of matrix, and you find the eigenvectors of the coefficient matrix. The principal eigenvector gives you the solution. It is exactly the same way the way you do steady state analysis for random walks. So, if you are interested, you can go and check it out, but anyway the basic assumption is this, that you assume that the degree distribution does not change, and you can write it as something like q star 1, and then you can try to solve this. This is one method. A very related method is like, since it is in the discrete domain, sometimes it is difficult to solve. So, you change it to continuous domain, you assume that T is continuous and you make a differential equation out of it and solve it, but of course with the same steady state assumption. And when you solve it, what you get is something like this. Now, it is slightly involved, so I am not going to solve it. It is very similar to the way you solve Barabasi-Albert model or the Simon model. All of these models are related, and you get something like q of q. So, remember we wrote it for only 1, we did not write it for general k. The case of k greater than 1 would be different, because this plus m term will not be there. So, there will be a subtraction term and an addition term, but the plus m term will not be there. So, it is there will be 2 equations and you have to solve these 2 separately, and ultimately you can write something like q as a function of q plus some constant to the power some constant. So, therefore, it resembles a power law, and by the way this is proportional, because you have to normalize it properly and to get the equality. And this particular exponent gamma is 2 plus the ratio of new actors to the ratio of old actors. So, if you change this ratio, mu minus m is the ratio of the old actors, the number of the old actors chosen, and m is the number of new actors chosen. So, this is this ratio. So, one thing you can note is this gamma is always greater than 2, because this quantity is always going to be positive, and how much greater than 2 depends on how many new actors you choose. If you choose a large number of new actors, then you have really a very high exponent. And here you can see that it is not q to the power minus gamma, it is q plus some term to the power minus gamma. This is the term which kind of so if you plot this graph in the log scale, rather than seeing this would have been the case if it was q to the power minus gamma. Since there is a addition term, you will see some deviation in the initial part of the graph. So, that deviation is due to this extra factor, and from this it is fairly easy to derive Pk. Capital Pk, what do? You replace q by k by mu minus 1. Remember, q is equal to k is equal to q into mu minus 1. So, you just replace q by k by mu minus 1. So, you get k plus this term into mu minus 1, because you have taken out mu minus 1 as a whole, 1 by mu minus 1 out of this expression. So, getting Pk is pretty simple once you get q, the function q, and after that it is pretty simple to get clustering coefficient and many other things. We have already seen the formula in the last class, and this is what the theoretical predictions are. Now, the question is, does it really explain the degree distributions that we have observed? So, in this graph, this is the one mode projection comparison. So, comparison of capital Pk for movie actor collaboration network. So, these circles are the real data, empirical data. So, you have got it from some sampling some real movies, building a real movie actor network and really counting how many actors per movie and all. So, you have drawn this particular distribution by constructing a real actor-actor network. So, this green line that you can see is the theoretical prediction, this green line, and you can see that it does not match very well, but it can explain at least this middle part which looks like power lawish. And this blue thing is so remember during the theoretical analysis we did a lot of assumptions. We assumed that this tends to this, and we assumed that the number of actors in all movies is same and all this, which are not really valid. So, if you do not assume all these things, you can't solve the theoretical model, means in the sense that it becomes very hard. However, simulation is not difficult. You could still simulate the model without making all these assumptions. You could think that n is randomly sampled, m is randomly sampled from a distribution, and you can simulate and using a computer program and see what degree distributions emerge, and if you do that you get the blue line. So, clearly the blue line is slightly better fit than the green line. This you concentrate on this part, it has come closer to the real. Although this end part it's same as the green line, it's there is a difference here. Otherwise the fit is good. Now, the question is what this difference really tells. So, this part we may not be worried so much. What is the fact that this difference is telling physically? What is happening in the model which is not the case in real life? Can you tell me? So, come up again.
We knew that the number of some comedians act more number of times with the most popular actors.
Right.
Means they have acted so much that the people have got bored with them. Or
so what you are trying to say is what is happening here is this blue line is predicting that the highest, the maximum degree of an actor node can be pretty high. It can be of the order of 10 to the power 4, whereas the real data is showing we hardly see any actor with more than say 5 into 10 to the power 3, something like 5,000. And one way to explain this, as one of your friends is suggesting, is that people get bored of seeing the same actor again and again, and so therefore the true preferentiality does not happen, it drops. Yeah. So, what you said, the basic intuition was right, but usually it is not because you are bored, but because the person is growing, he is getting older. So, naturally here the nodes can stand in the network forever, but that does not happen in real world. As you grow older, even if you get thousands of movie assignments, you do not have the power to work in all of them. So, for fixed lifespan, the degree of co-actor degree can never be infinity, it can't go to infinity, but in this case if you simulate it for infinite time, the degree will the maximum degree can increase like anything. So, we showed that the average degree is constant, but we never showed any bound on the maximum degree. The maximum degree goes on increasing, that is what it is showing, it goes on increasing, but that does not happen in the real world, that can't happen, simply impossible, because the person will age and finally die. So, then they modeled this concept of aging in their network. So, every node when it comes with an age tag, and at every time step its age also grows, and there is a so from the preferential term you subtract a small term based on the aging, and eventually that node might disappear in the sense the node will be in the network, but the negative factor due to aging will override the preferential factor. So, that particular node will get no edge incoming connection in the later stages. Now, this model is quite difficult to analyze because you have one more factor, not only the preferential attachment, and therefore, they only simulated the model. This is the Ramasco paper that I am talking of. And then you get the red line, which seems like even a better fit. So, this part at least matches to a better degree. So, this is what I had to say about the Ramasco model. Now, the question is, we ask is it the case that all networks, all bipartite networks whose examples we know, which we encounter in nature, in natural systems, will follow this model? Is it the case? So, what is the problem with this model? So, this is the problem. Remember the first day I gave you the example of codon gene network. So, what happens in a codon gene network? How many codons are there in total? There can be only 64 codons. Think of the word letter networks. How many letters can be there? Only in case of English it is 26. In case of some other languages it can be very high, say Chinese or Japanese, but does not matter how big an alphabet is, but it will be always finite. For any language the alphabet set is finite. So, what is the concept that is there in the Ramasco model that does not apply to this kind of bipartite networks? Which part is not true? So, the Ramasco model assumes that every new node comes in, chooses m new actors and mu minus m old actors. This m part does not hold clearly. So, you can't go on choosing new actors. So, a gene cannot come tomorrow and choose a 65th codon, because there is no 65th codon, there are only 64 codons. A new English word can't tomorrow appear having a new letter, a 27th letter, it is not possible. So, there are cases of bipartite networks where one of the partitions is fixed, it does not grow with time, the other partition grows with time. So, if we study those networks, is there any fundamental difference in the degree distribution that we observe? That is the first question. Can we propose a model for them? The second question. And if we analyze the model, is there again any fundamental difference? So, the earlier model, the Ramasco's model, we saw generates power law degree distributions. So, is it the case that this model also generates power law distributions? These were all the interesting questions that naturally arise. So, this special class of, so we thought we will study it. Why I am saying we is because this is a work that we had done recently, we are still working on it. So, we named them alphabetic bipartite network. Here why we call alphabet is to give a sense that the set is finite. Alphabet is a set of letters which is always finite. So, you can think of it in this way, there are letters which makes words. So, there are fixed number of letters and a word has letters maybe with repetition and words form the other partition. The partition of the letters is fixed. What about the partition of the words? It can grow, but does it grow infinitely? Are there infinite words in the in a language? So, there is a big debate about it. It is not so easy to say whether a language has infinite words or not. Most of the theoretical analysis show that languages indeed have infinite words. There are many predictions, and the reason I will tell you, think of so how do you know how many words are there in a language? What you do, you take a corpus. Corpus is a set of running text, and you read it one by one and see every word. If that word is already there, that is an old word, otherwise the word is new and it goes into a new kind of set, means you add it to the set, and this process continues. If you continue this process, actually you will see that new words keep coming, no matter how big a corpus you look at. If you take all the newspapers, everyday newspaper published from say some 1800 till 2000, you will still find the next day there might be one or two new words, and typically these new words are names of people, places and lot of other things that you encounter. So, there are other consequences of this actually. So, if you know, have you heard of Zipf's law? So, there is a law called Zipf's law. If you count the frequency of the words in a kind of corpus, it shows a perfect power law, not even a distorted power law, it shows a near perfect power law, and this was identified as early as 1930s 40s by Zipf. So, it is called as Zipf's law, and it is true for all languages in the world. This is a very interesting and unique property of natural languages. I should not say unique, because many other natural systems show power law behavior, but all languages show this particular behavior. So, this behavior will be captured in the second actually network. So, here are sentences and here are words, and sentences come in and you attach them to words. So, this is also another bipartite network, but in this network, as we shall see later, if this partition was really fixed, you would have never got perfect power laws. Perfect power laws never occur in alphabetic bipartite networks under no situation. So, it can occur only if one of the both the partitions are unbounded, as in the case of Ramasco. So, movie actor network. So, therefore, this network has to grow actually infinitely, but that apart, there is also another interesting thing. The letters are completely fixed. This grows, but we have an intuition that this should not grow very fast, whereas the number of sentences will grow very fast. Take a corpus, every other sentence will be different. You will hardly encounter the same sentence again. So, you have a huge space. So, this really grows very fast. So, you see there is a difference in the growth rate. This is the growth rate here is 0, the growth rate here is maybe fixed, but quite slow, and the growth rate here is very high. So, we perhaps could consider this is definitely an alphabetic bipartite network, because one of the set is fixed, the other set is growing. Here, although both the sets are growing, perhaps we could consider as alpha bin, we do not know, because the growth rates are very different. So, maybe we could consider that this is almost fixed. So, those are interesting issues, but what happens when we have a case like this alpha bin? How the growth rate, how the growing rule, the evolution pattern changes. So, we need to change the model a little bit. We do not have the extra m coming in. So, we have all the nodes in this partition to start with, and now think that a new word comes into the picture, and it has to choose all the letters from the old ones. So, it will choose all the letters preferentially. That is the basic Ramasco model, but it will not choose any new model, any new letter, it can't choose any new letter. So, it chooses preferentially. So, we could have said it chooses with this k plus sigma k, right. What is the problem there? Why are we adding this epsilon term? You got the point. So, k is the degree of a letter. That is one way to answer it. This epsilon adds some randomness. It's not the preferential part. So, if epsilon is too high, you will see the network is almost like a random network, but there is another reason for doing it also.
For setting the initial condition.
Exactly. So, think of initial, suppose the first 10 letters you have seen had no z. So, the degree of the letter z at this point of time is 0, but then it will remain 0 forever, because you are doing 0 by something which is always 0, and z never gets a preference to be in any letter. So, be in any word. So, that is the problem. So, to give the initial thrust also you need an epsilon. So, in different literature community, this epsilon is known by different names. For example, in machine learning this is called smoothing. This epsilon is kind of a smoothing, but the other interesting part is this epsilon is related highly to randomness, we will see in a moment. But before that, let us just briefly discuss 3 sub cases, 3 possibilities of this basic model. First possibility is sequential attachment. At every step only one edge is added. So, essentially what we are trying to say is mu is equal to 1. Remember, every word node or movie node chooses mu kind of actors. So, in this case I will take the analogy of word letters. So, every word node chooses mu letters, but if mu is equal to 1, essentially adding every node at a time means adding an edge in the network. Every node has one edge. So, this is one possibility, and there are many examples of this kind of network in the world. Can you think of one? P2P networks are not typically bipartite networks. All the nodes are of the same type. So, one possible example, anything which has to do with set membership is this kind of a network. So, what I mean by set membership is this: all of you have a mother tongue. So, if in one set you have all the languages which is nearly fixed at this point of time on earth, certain number of languages are spoken. So, let all of them be known, and every time a new person is born, the edge I attach is to his or her mother tongue, then it is a single edge. So, although you can think of native bilingual speakers and all these, but if we do not complicate the case and all, there will be just one edge added at every time. So, this is one. So, citizenship, in which country you were born, and all these are interesting because if you study demographics, how the population of the different countries or the speakers of different languages have changed over the time, this model really helps. We could show that. The other model is what we call parallel attachment with replacement. So, here mu is greater than 1, but the word node can choose the same letter node again and again. So, the same word node. So, in the case of movie actor network, the hidden assumption is the same actor does not act in this movie more than once. It does not make that much of a physical sense, but in a word the same letter can repeat. It is very common. So, this is parallel attachment with replacement. Why we call parallel attachment? Because mu edges are thrown into the network parallelly, and why we call with replacement? Because choosing one node, choosing one letter at a point does not prohibit us to choose the same letter again. So, we put it back in the set and can choose in the next step and so on. And the third case, so even gene codon is an example of parallel attachment with replacement. And the third case is parallel attachment without replacement. So, I have to enforce that all the different mu units that I am choosing are all different, and this happens in some other cases, like when what I am choosing is a set rather than a sequence. A sequence can have repetitions, but a set cannot. So, one example is what vowels are used in a language. So, I am not looking at the frequency of the vowels, just that what vowels are used in a language. So, there are many such examples that come from different biology as well as like what proteins are used in a protein complex. So, it does not make sense to say that the same protein is used more than once. So, it is a set of proteins that are used. So, all these are minor variations, but even though they are minor variations, the mathematics is entirely different, and although the first case you can solve exactly, the second case one can solve approximately, the third case even approximate solution is a bit difficult. So, I will show you the final solution how it looks. We are not going to solve it of course here, but there is one very important difference between how you solve this versus how you solved all the other cases you have seen previously, and let us see what is that difference. Suppose T is the number of nodes in the growing partition, is the same. So, at every time step you introduce one new word, that is the T. So, Tth word. So, T is the number of words, N is the number of nodes in the fixed partition. So, fixed partition is total number of letters. So, that is N is fixed, and we note that the degree distribution is. So, there is a slight change in notation. I apologize for that. So, in earlier one we used Q for the bipartite and capital P for the one mode. Here we are using P for the bipartite itself. So, just bear with this. Keep in mind that here P means the bipartite network degree distribution. So, at time t was the probability that a node has degree k. But of course, we are looking at these n nodes, the degree distribution of these n nodes. These are not interesting. All of them have mu edges, and mu we can assume to be 1 or anything. But suppose all of them have mu edges. Now, tell me what is the average degree of a letter node in this bipartite network. So, how many edges are there in this bipartite network at time t? Mu t. So, number of edges is simply mu t, and how many letter nodes are there? N. So, what should be the average degree of a letter node? Mu t by n. So, now do you see any problem in this system? What happens to the average degree as t grows? So, can you assume a steady state here as you did in the last case? Can you ever assume that something like p k t is equal to p k t minus 1 is equal to p star k, something like this? You can't, because the degree of the mean degree of this is different from mean degree of this is different from mean degree of this. So, if this was the case, at some point of time the mean this will be the case if the mean of this distribution is same as mean of this distribution. It has to be, right, only then the distributions are equal. But since the mean itself is not equal, it changes from at every time, it diverges, you can never write this. So, this very strong tool which is used always to solve these recursions can't be used here. So, this is the insight I wanted to give you. After that, it is pretty like standard thing. The initial condition is we assume that all nodes in the fixed partition has 0 degree, and so this is what it precisely tells. So, all nodes have 0 degree. So, P 0 is 1, whereas P k, where k is greater than 0, is 0. And then you write the Markov equation. I will not go into the details of how these Markov equations come. It is exactly the same way, in the sense that one part of it tells you how many previous nodes with degree k goes to k plus 1 in the step, and how many nodes with degree k minus 1 gets one edge and comes to degree k. So this is the term with how many previously had k minus 1, but now got an edge and became k, and this is the subtraction term. This one is for how many there were and still remains, and so on. So, you have this Markov equation. Unfortunately, you can't use the steady state condition. Solving this becomes a bit problem, but still with some other linear algebra techniques and all, finally it could be solved, and the solution looks something like this. So, if you look at the exact solution when mu is equal to 1, you get this product terms on the top, and this is a combinatorial term. This whole thing, which looks like extremely cumbersome, is there is a nice name that mathematicians have given it. They call it a hypergeometric series, but it is like very difficult to get a single simplified version of this without any approximation. So, if we do some approximation, Stirling's approximation, which you do typically for factorials or combinatorial terms. So, if you do Stirling's approximation of all these terms, you get a much better form, and this is something like k by t to the power epsilon minus 1 and 1 minus k by t to the power this n epsilon minus 1. This thing is a very standard distribution in probability and statistics. This is called beta distribution. So, beta is a family of distributions. Actually, it is not a single distribution. Even normal distribution is a kind of a beta distribution under certain properties. So, when one of them when both of them are equal, it goes to binomial distribution and so on. So, there are several properties of beta distribution. This is nothing but the normalizing term. So, rather than looking into the formula, because I do not think it is going to help us much, let us look at the curves, how they look. So, this is how the degree distributions look, and there are clearly 4 different types of degree distributions that emerge. So, the first case is when epsilon is very, very high. So, in that case, it is almost like random attachment, right? The degree does not get any preference. So, in case of random attachment, we get a distribution like this. So, what does it resemble? A normal distribution. So, this is just like a normal distribution. When epsilon lies between 1 and some very high, it is between it is more than 1, but not very high, substantially bounded like 2, it looks like a skewed normal distribution. So, when you ask somebody what is a beta distribution, they will probably draw this picture. This is the most common picture that you look at when you look at beta distribution. So, it is skewed. The both sides are not symmetric. This side is still longer. So, you have much higher degrees in the graph. Lower degree nodes are large number of lower degree nodes, but the high degree nodes are few, but the max degree grows. So, it is going towards skewness. A network is skewed if it has a few nodes with very high degree and large number of nodes have very small degree. So, this is a very fair network, not at all skewed. Most of the nodes have the average degree. Here it is still true, but it is going towards skewness, and this happens. This is an exponential degree distribution. It occurs at epsilon equal to 1. Actually, if you look at the previous thing, at epsilon equal to 1, this term vanishes. Only this term remains, and this can be approximated by an exponential distribution. So, what happens here is mode is at 1. What it means is most of the nodes in the network has only degree 1, and mode is at 0. So, only degree 0. Here nodes, there can be nodes in the network with degree 0. Remember, because we started with all nodes having degree 0, and this epsilon was mainly added to solve this problem of degree 0. So, at the end of the simulation also you can have nodes which has degree 0. So, this is what is happening. Lot of nodes, actually always majority of the nodes have degree 0 in this case. And this is the final case. It is very interesting when epsilon is very, very small, the situation is highly preferential. You have some nodes, say 2 or 3 nodes, which takes all the degrees. So, they have very high degree. There are no nodes in the middle zone. So, no nodes have degree say 60, 70 or 80, rest of the nodes have degree 0. So, it is a U-shaped distribution. So, there are only 3, suppose the network had 1000 nodes, 3 of them have degree 1000 at the end of the simulation and 997 of them have degree 0. So, this is something like winners take all situation, means it is closer to that. So, there are few winners and they are taking all the edges that are coming, and in real world you could find examples of all these, at least all these 3 cases. This one we are still looking at if you can find some nice example. And one last thing, what happens with time, since this is not a steady state distribution, as time progresses the shape of the distribution changes. So, clearly if at a smaller time, say at time step 100 it was like this, at a larger time it goes like this, and even larger time. So, what is happening is this mode at 0 is dropping. This is for a low epsilon. So, something like epsilon less than 1 or so. So, finally, it will come closer to the normal skewed beta sort of, whereas the u will grow like this. So, among these 3 curves, which one you think is time less and which one is at a later time, which one is at the earlier time and which one is at a later time among these 3 curves. So, this is say curve 1, this is curve 2, curve 3. Curve 1, right. So, curve 1 is at a smaller time, you can say that because its max degree is small, whereas as the time proceeds the max degree goes up. So, the u changes.
The approximation also holds better.
Yes. So, these red lines are the lines that are approximations. The blue dots, as you can see, the blue circles here are what we get from the simulation. Okay. And when we try to match it to certain real world examples, we could really see that earlier what we thought were power laws were not power laws, but much better fitted with this kind of beta distributions. But again the story goes on. So, you have so do you know of superlinear kernels, superlinear preferential attachment. So, if you do a superlinear preferential attachment here, something like k power alpha plus epsilon instead of k plus epsilon, where alpha is greater than 1, you get even more rich class of distributions, which is difficult to characterize mathematically, but we could see at least in principle, means by simulation. And finally, what's the physical significance of epsilon? It's the amount of randomness in the system. The actual significance depends on the specific system you are looking at. So, if it's like if you look at the internet and try to find out the distribution of people over the distribution of the web pages versus languages. So, how many web pages are there in English, how many web pages are there in Hindi, and how many are in Tamil, and so on. So, what do you expect, that system to have a large epsilon or a small epsilon? So, here the network has 2 partitions, one partition is languages, one partition is web pages. New web pages come in and attach themselves to languages. So, mu is equal to 1, because typically a web page is written in only one language. So, if you simulate this system, if you study this system, what do you think, the epsilon will be high or low? Why do you think the epsilon will be low? Right. So, here the distribution is almost like the U-shaped curve. So, there are 3-4 languages on the internet which dominates, English, Chinese, nowadays English, French, German, and nowadays also Chinese. So, these languages, Spanish and little bit of Arabic, takes all the web pages, but if you look at Hindi and all, Bengali, Tamil and all, they lie in the middle zone. So, it is not that the middle zone is 0 almost, but there are numerous, there are about 7,000 languages. So, only say 50 of them you could see even a web page, rest of them you do not have any web page, virtually 1 or 2 web pages maybe. So, the 0 thing is very high, lot of them have 0 degrees, whereas there are systems like Wikipedia where this Q is not so high. So, if you look at the same data on the Wikipedia, how much people are contributing, you get a much fairer, of course not very fair, not a normal distribution, still English is very high, but you see a fairer distribution. So, this significance of epsilon depends and varies from system to system.
So on Wikipedia shouldn't be fair because it should depend on only the amount of the population percentage.
Right. So, the population percentage, the distribution of the population is actually much fairer than the distribution of the documents on the web. This is the first thing. In fact, it is one of the most fairer systems, although I am not saying its epsilon is greater than 1. So, it is definitely not this case or this case, it is similar to this case. Of course, the peak is of course not at 0, the peak there has to be one speaker for the language to exist if we look at only current languages. However, it is closer to this, but still epsilon is not so small, it is not closer to this. It is something like epsilon is say 0.5 or okay, let me show you, I think I have the data, right. So, for speaker the epsilon is something like 3 into 10 to the power minus 3, which is not that bad actually, but for the web it is 10 to the power minus 4, it is order of magnitude smaller. So, the web is the less fairer than the speaker distribution. The wiki actually is almost as fair as the speaker distribution as you suggest. Since the speaker distribution, the web is actually controlled by economy more than the speakers. Not E, it is a way of writing 2 into 10 to the power minus 3. Okay. Any other questions? Okay, so we stop here for today.